Welcome back. I hope you had a chance to have a cup of tea, and I hope you're okay with the principles of light and electron microscopy. Now we're going to look at atomic force microscopy, which, as I've said a number of times, is a completely different type of microscopy. It's not illuminating your sample in any way. In fact, I'm not really sure it should be called microscopy, but it is, and so we're going to consider it in this lecture. So the way that atomic force microscope works is you have a really fine tip. So that could be machined, or more commonly it's made with silicone, so same sort of processing techniques as you might use for making silicon chips, for instance. But in principle, you make a tip which is almost atomically thin at its point. So imagine I was to sharpen a pencil and I made it really sharp at the point, and that point was just a few atoms thick. That's essentially the tip of an atomic force microscope. It's mounted onto a thing called a cantilever, so a cantilever can move up and down, and on the back of the cantilever there is a mirror at an angle. So the way the atomic force microscope works is it takes a laser and it shines that laser at the cantilever tip. It's focused on the mirror, and so the mirror will then reflect the laser beam back to a detector. The reason it does that is because as you put the tip in close contact with your sample and you move it, if your sample is rough, the tip will go up and down over the contours of the surface of your material, but that movement is really small. By shining a laser onto this mirror and measuring the laser deflection, that movement becomes amplified. So imagine that the laser's up here, is shining off the mirror, and the reflected laser beam is also shining on the wall. A small movement here corresponds to a large movement on the wall. That's essentially how an atomic force microscope measures the position of the tip. Then what you do is you take your sample, which is pretty small, it's got to be said, normally maybe 100 microns by 100 microns. You bring your tip down onto the surface of the material and you raster across the surface of the material, same as at SEM. So you go in one direction, measuring the Z deflection, then you move, you go over the surface again measuring the Z deflection. So you should end up with an image which is X, Y, Z. Okay, so it's a topographical image of the surface of your material. This is just a diagram to show you in principle how this works. The image on the bottom left is an actual SEM, so you should be able to know this by now because it's grayscale. SEM image of the tip of the microscope. You can see it's a very fine tip, almost like the needle on a record player, for instance. And then on the right hand side it simply shows you a schematic of how that's working. The tip's moving across the sample, the laser is shining onto the back of the mirror, is being reflected and is being detected, and you move the tip across the sample in an XY pattern and measure the Z. Just one thing to note here, it is possible to make these measurements in a slightly different ways by tapping. So imagine that your material is very hard. You can bring the tip down and you can bounce the tip up and down off the surface of this material. And if this is a truly elastic solid, then the tip will always bounce back to where it started. But if it was a more elastic solid and you bounce, then it becomes damped because the material is starting to absorb the energy from the tip. So by measuring how the tip responds as it's bounced across the surface, you can tell something about the mechanical strength of your sample. And then to image your sample, you simply bounce the tip at one point and measure how the signal is decaying. Then you move the tip to another point and do the measurement again. So you're still building up a topographical image, but now it's point-based as you move across the surface of your sample. So there are some benefits of AFM, otherwise it wouldn't be used, right? So the main benefit of an AFM is it's not shining electrons onto your sample, because electrons are extremely damaging, as I said already. So in this case, it is just the tip of your material which is being moved gently over the surface of your material, so it's non-destructive. I didn't say earlier actually, and I probably should have done, but for an electron microscope, it's got to be operated in a vacuum, because if it's not in a vacuum, the electrons tend to interact with air and they don't get to the detector. So you have to hold your material under a vacuum. And in addition, you've had to cover it with a heavy metal, and so you really have sort of damaged your material, especially if it's a wet organic solid. It's now under vacuum, which has dried it out, and it's covered in a heavy metal, and that's not good. You don't need either of those things for an atomic force microscopes. It's much better for organic samples because you can just sit them under what would be more ideal conditions, and you can make sensible measurements. It's also possible to control the temperature and the humidity that your sample is sitting in, and the reason is because the actual AFM itself is quite small. It's just a motor moving this tip plus your sample. So you can put all of that into a box, and when you can get things into a box, you can temperature control that box and you can control the humidity. So you can do things like increase the humidity and see what happens to the sample, or increase the temperature and see what happens to the samples. It's quite a useful technique. Probably more importantly, you can even hold your sample under the surface of a liquid. So let's say you cover it with water, you can still bring the tip down through that water and image underneath the water. As long as you don't move the laser beam too much by refraction, you can still make the measurement under a solvent. And that can be really useful if you're trying to ask questions about how does the surface of my material change as it gets wet, for instance. And especially if it's a milled powder for a dry powder inhaler and you're conditioning it after processing, you might want to know how wet do I have to get this to make it crystalline, and that may include physically getting the surface underwater. The images on this slide are two very interesting images as far as I can see, both made with an AFM. So you've got two images, one on the left, the pink and blue one. That's an interesting looking one. It's quite regular, doesn't it? I'm going to let you have a little guess as to what you think that might be. And then the one on the right is colour-coded red for a reason, actually. So I'm going to give you a few seconds just to look at those images and think to yourself, what might they be? I would ordinarily have a drink at this point, but I'm in the laboratory, so I can't. It just means I'm going to wibble at you until you've had a think. Had a think? Okay, so what do you think the sample on the left is, the pink and the blue? Got any idea? So if you look at that, I don't know whether you can see, but you've basically got long lines and short ones, or as we like to call them, dots and dashes. So it's essentially conveying information. So that is actually the surface of a CD. And it's the way that the information is burned into a CD with a laser. Okay, the laser is burning either long holes or short ones, which represent ones and zeros. And so it's recording digital information with ones and zeros. So that's what the surface of a CD looks like. And the reason they're all in line is because CD is read in circles, so you've got almost concentric circles with the information on. What about the one on the right? Got an idea what that might be? It's coloured red for a reason. The answer is they are red blood cells, actual red blood cells from a human patient. Yeah. So I don't know if you can see that, but each one of those is an individual red blood cell. You can see the concave surface. So you can image to pretty good resolution with an atomic force microscope. The last thing it says on this slide is you can also modify the tip to measure thermal conductivity. So I first came to the school in 1997 as a postdoc, and I came here as a postdoc because one of the research groups here is being led by Professor Craig, who's the dean at the moment actually. He was actually one of the first in the world to use atomic force microscopes with thermal imaging tips, and I'm a thermal analyst by trade, so I actually came here to use this type of microscopy. So I'm going to look at it in just a little bit of detail because I find it quite interesting. So the way this works is the tip itself is made of metal, and because it's metal you can pass an electrical current through it. Okay, so if you pass a current through it, you can measure the resistance of the tip. If you bring that tip down onto the surface of a material, if that material is not conductive in any way, you can pass current through the tip, nothing will change. But if that material was, say, a metal or something that was conductive, and you bring the tip down, some of the current that you pass through the tip is now being taken away by the material. And so the amount of current that you've got to put through your tip to maintain it changes. And so by measuring how much current you're putting through the tip, you can tell something about the thermal conductivity of the material on which the tip is resting. And then what you can do is you can, again, move the tip over the surface of the sample and measure the thermal conductivity of your sample at various points. And in that way you can build up a topographical image on thermal conductivity, not just on Z position. Okay? So the example in front of you is a single liposome in water, and it's being imaged. And so in this instance you've got height, Z, on the box. So the height above the baseline for the AFM is being colour-coded. Dark brown means it's at the baseline, and it goes all the way up to white, which in this case is a height of 65 nanometers, 65 nanometers, that's very small. You can see that the majority of that topographical image, so that's an X and Y on the image, it's all brown, which essentially means the tip's at a zero, null position, it's at a baseline position, except for where the circle is, where this liposome is, and you can see yellow moving to white circle, which kind of indicates that there's something there. One of the beauties about atomic force microscopy is that the images you're presented with are these grids, and so it's possible to use software to have a little analysis of that sample. So in this case there's a black line going across that circle, and that's part of the software. You can put a line across various parts of the image, and you can ask the software to plot just the Z dimension. So if you do that on the next slide, this is the Z dimension for that liposome, and you can see the tip was essentially at zero and then went over that liposome. So you start to get a real idea for what's the physical size of these individual liposomes. It's kind of scary, the resolution you can get down to with an AFM. Right, this is the tip that I was just talking about, which has been modified to measure thermal conductivity. It's essentially just a wire which has been insulated, and the insulation has been removed right at the tip, which is where it touches the sample. So it allows you to measure thermal conductivity. So this image is indomethacin in a tablet, and so the way that works is indomethacin particles mixed with excipients and then compressed into a tablet. And the question is, where is the indomethacin in the tablet? Is it discrete particles? Did it blend well, or whatever? So the big image is simply showing you the topographical data as recorded by the AFM for that tablet, and you can see it's relatively smooth, and there's just one bit that looks a bit high at the back, which is in yellow, so it looks like something is sticking up. If you then make a thermal conductivity map of that sample, which is the smaller image towards the bottom, then you can see that the majority of that tablet is colour-coded yellow-orange, and there's one region which has got a sort of darker brown blob, for want of a better word. And so that's kind of implying that there's something there which is different. Most of the tablet is homogeneous, but there's something stuck in the surface of the tablet which is behaving in a different way. Can we try and interrogate the surface of these materials and try and work out what that is? So in the indomethacin tablet, the chances are that's a particle of indomethacin exposed at the surface of the tablet, but other than saying it's got a different thermal conductivity, it's quite difficult to say for certain that is definitely indomethacin. One of the beauties of this type of tip is that it's measuring resistance by passing a current through it, and you can measure thermal conductivity in this way. But as I'm sure you're aware, if you pass a current through a metal wire, it heats up. It's the principle of how your toaster toasts your bread in the morning. And this works the same way. You can increase the temperature of the AFM tip by putting more and more current through it. And what that allows you to do is to make almost like a DSC measurement, or it's not really a current measurement, you can mimic the temperature profile of a DSC while you're making a measurement at the surface of your material. So imagine this is your material, the tip comes down, you can place that tip on the surface of the material and measure its Z position, but then you can increase the temperature of this tip, and what that will mean is if you increase the temperature but you haven't gone above the melting point of the material that's underneath it, the tip will remain in place. But as the tip temperature goes above the melting point of this material, it will melt, and as it melts the tip falls into the material. So by measuring the Z position and measuring the temperature, you can actually measure the melting point of the material that's underneath the AFM tip. Clever, huh? So here are some examples of indomethacin tablets again. So you look at the two images on the left-hand side. They're two separate images of the same compact. Now, I've said many times, crystalline material tends to look as though it's got sharp edges, and amorphous material tends to look rather smooth. So I think in this case, it's indomethacin in a polymer. The indomethacin is crystalline and the polymer is amorphous. So if you look at the top image, most of that image looks as though it's crystalline. So it looks like there's a lot of drug at the surface of the compact, but there's one region in the top left-hand corner where it looks quite smooth. So it looks like that might be polymer. LTA stands for localized thermal analysis. It's where the tip was placed and heated up to measure the melting point. So you've got LTA 1, 2 and 3 at the top of that image, And if you look on the graph on the right hand side, you can see that LTA1 and LTA3, nothing melted until about 160 degrees centigrade, so that would confirm the presence of drug. Whereas LTA2, which is where on the smooth surface, it melted at around about 70 degrees, and that's because the polymer had a much lower melting point. So you can move that tip to various points on the surface of the material, heat it up and measure the melting point, and you can see exactly what's going on with your sample. The bottom image is the same compact, it's just a different part of the surface. Now you can see where LTA1 looks crystalline, and LTA2, 3 and 4 look rather amorphous. And again, if you look at the graph on the right hand side, you can see exactly that. LTA1 measures at 180, melts at around 160 degrees, and 2, 3 and 4 melt around about 70 degrees. So you can move the tip across the surface of your sample and start to tell things about what is there. You can now buy tips from manufacturers with really good resolutions. This is just an image of the latest generation of micro TA tips. Now you can see you can get down to nanometer resolution. So not only can you ask questions about what material is there, what's its melting temperature, what's its thermal conductivity, you've also got resolution down to nanometers. The last slide in this whole lecture says spectroscopy, and you might say to me, why is spectroscopy in a microscopy lecture? It's a very fair question, actually. The reason is because atomic force microscopy, for instance, isn't using light to illuminate your sample. It's using a probe to touch the surface of the material and build up a topographical image. And that's really the key for microscopy, right? It's building up an image map of the surface of your material. And I realised that we do the same thing with spectroscopy. So typically, we use Raman microscopy, Raman spectroscopy to map our samples. So this is an example I may have shown you in another lecture, but it's one of my favourite things with 3D printing. So we printed two types of capsules with the 3D printer, both containing two drugs. So on the left-hand side we had a multi-layer tablet, and on the right-hand side we had a core and a shell tablet. And in both cases, one of those layers contained paracetamol and one of them contained caffeine. Okay? So the question is, how do we image what we've made with the printer and work out where the drugs are? And we do it with Raman mapping, and it made me realise it's essentially an imaging technique, so I thought I'd just mention it here. So we cut those tablets in half, so we're looking at the cross-section of each tablet, and then we use a Raman laser. So the Raman fires the laser at the surface of the material, and the laser is reflected back to a detector. And the wavelengths that are reflected back are different from the ones that hit the sample, because the sample is absorbing some of the light. And so you can get a spectrum from each point at which you move the laser across. And again, like AFM, especially in tapping mode, you simply move the laser to various points on the surface of the material, measure the spectrum of absorbance at each point. If you know what the reference absorbances are for your two drugs, in this case paracetamol and caffeine, then it's possible to colour code the images that you get. So in this case the images are colour coded red for paracetamol, green for caffeine. And you can see that on the left hand side we have paracetamol, then caffeine, paracetamol, caffeine, matching the multi-layer tablet. And on the right hand side we have paracetamol in the core and caffeine around the outside. So I simply put this here only because it made me realise that actually, because you can use AFM, and that's not really illuminating the sample, there's all sorts of other things that you might not necessarily consider microscopy, but they are basically imaging, and so therefore they probably should be considered as a microscopy. And Raman mapping is one. Right, that means we're at the end. You'll be pleased to know. So that means once I've told you what the summary is, and you need to know from this lecture, you're free to go and get on with your day, which is tremendous, isn't it? So, remember what we talked about. There are three common microscopies where we're illuminating samples: light microscopy, transmission and scanning electron microscopy. They are the same in principle, it's just that light microscopes are using photons to illuminate your sample and lenses to manipulate those photons. The electron microscopies are using electrons to illuminate your sample, and are using magnets to focus to create the image. Both can be configured in either reflectance or transmission modes. You need to be very careful with electron microscopy for that. If it's in reflectance, then it's scanning, and you're scanning the electrons across the surface. and if it's transmission, then it needs to be a very thin sample. Light microscopes can be configured with hot stage or cross polarising filters, and that really allows you to interrogate the physical form of the sample. And AFM is a completely different type of microscopy, and it's just imaging surface topography. Right, with that, we're done.